All right, so our question says, so I guess we have to use the notes because it says use page 164 as a guide.
That's
But we're
the
giving
textbook, right?
the E1 mechanism
Her notes.
for the reaction of the molecule. Oh, we have to do
I don't know what page that is. Which one is it? Is that in topic 10? Topic 10?
Yeah, topic 10.
They're not numbered on here.
So we have to do it with the molecule above. So the
They're
potassium.
not numbered.
So first we redraw the molecule above, which is I didn't name it.
Like a
It's a
cyclohexane ring with a chlorine going into the page and two terbutyl groups.
And two terbutyls.
Yeah, they're coming away from the page. A solid wedge. My pages are not numbered. Is there pages numbered?
So
That means we have a hydrogen right here.
Yeah, going away.
So the alpha carbon is the carbon that is connected to the halogen, which is the chlorine atom, and the beta carbons are the carbons connected to the alpha carbon, which is the carbons connected to the tetrabutyls.
But the chlorine leaves, right?
yeah, but that's
So your leaving group,
Wait, hold on. Wait. We have to put the hydrogen.
On both of them. Both terbutyls have a hydrogen.
you have to show them. Yeah.
Maybe helpful later. Okay, and
So go ahead with the leaving group.
is the chlorine atom.
So, I mean, that's the electrophile.
and then the base we chose what? Potassium hydroxide. That's what's in the problem.
And this is the electrophile. Let me label this.
So the carbon just leaves
EU.
bonds with the H.
So then,
Reacts with potassium hydroxide.
Yeah.
all right. So the KOH. Oh, because that's what they told us, right?
Yeah, that's what potassium hydroxide.
And this is the
Base.
neutrophile.
It's not. It's a base. There's no nucleophiles in elimination reactions.
And can you explain why?
Because nucleophiles attack the leaving group, the bases just like take it off. So nucleophiles will attack it and they'll switch. But
So that's why it's not in any of the end product. It's just gone.
so the KCl leaves and the potassium and the hydroxide break. So then you're left with just OH.
Well, something we know about E1 mechanism is that it's a two-step mechanism.
Oh yeah.
So there's going to be a slow and a fast step.
We can do that. If we can name that after.
So two-step.
Well, two-step process, I guess.
Because the first step was the slow step, right?
Yeah.
Two-step process.
Yeah, space or not.
He says slow
And fast.
and fast.
So the next step. We're going to space to keep writing.
Okay. So where did we leave off?
So we're starting off with the slow mechanism.
Okay.
So we have to show our intermediate step. Yeah.
Are you gonna draw it?
Yeah.
Okay.
Like this thing. You can't just go from
I'm
here
gonna
to
redraw
here.
the structure.
That's what slow is.
I know. We already did this part, so now we're going to this
And it's
part.
just
Yeah,
the
that's the
oxygen,
slow
the
mechanism.
hydroxide that's gonna bond. It's
That's
not
good.
the
That is
potassium,
slow.
right?
Go in here. That's slow.
I know.
That's why I was like, what do you mean? Like,
Oh.
They're not saying that.
Chloe, I didn't hear you. I was
said-
writing. I didn't hear you.
I said, so it's the hydroxide that's gonna bond with the H, not the potassium. The potassium is just not there. because it's
Potassium already
spectator.
bonded with the chlorine.
Okay, so this is the hydroxide.
The hydroxide will attack or grab the hydrogen on one of the beta carbons.
To make
Water.
yes.
Wait, no. Supposed to be the hydrogen, right? Does it matter which hydrogen it bonds to?
I don't think so. 'Cause I think they're identical.
It doesn't matter.
They're identical.
Yeah, they are identical. I was just making
Yeah, it
sure.
does matter.
I guess I'll give you two major products. But I guess not, because they're identical. But I guess it's only one
So they're
product.
one product. If they weren't identical, that means one of them would be a minor product.
So that means
Yeah,
the
but because it
OH.
looks exactly the same.
The OH has two lone pairs.
Yeah.
So that means oxygen has a negative charge. Right?
Yeah. And so
And then you gotta remember that the
then-
removal, or did you not write the CO? That
Do
is
we
gone.
have
We
to
already-
do
But you have
that?
to write the removal, it makes a positive charge over here.
yeah, on the
Like,
alpha
something we
carbon.
have to do.
Yeah, because E1 and SN1 both make carbocations. And they're after the first step.
Erase this first. Okay. Let me add this hydrogen back in a proper place.
Asking about regarding how the nucleophile and leaving group.
And this carbon has a positive charge.
Yes, because
Make a carbon cation.
So that means, so the electrons from this hydrogen,
Okay, so concerted means one step, all at the same time. That's concerted. That means one.
so this
If there's a
hydrogen,
transition state, if there's one transition state, then there's one step.
this hydrogen
Because if you
lose
look at
its
a
electron,
reaction,
or this
here's your
bond.
diagram, okay?
the hydrogen.
This is your
Oh.
starting material.
The electrons goes towards the carbon.
Transition state.
Yeah.
That means
And then the
Goes to that bond.
yeah. But then the electrons from
Wait,
the
what bond?
The
oxygen.
OH. This,
which means you have two
So
steps.
the oxygen has two lone
Where's
pairs.
this arrow going?
So the number of transition states tells you how many steps.
It's going to that bond. This is kind of hard to see.
oh, that's what I need. I need a smaller pencil. Yeah, it's going to this. It's going to this bond right here.
Oh, okay.
What's going to that bond?
The electrons.
This bond
Well, I
that
guess-
the hydrogen,
But the electrons in that bond.
Are going to that bond.
this one right here.
Because the chlorine left out, the bond for the hydrogen went to.
No. This is because of the OH. That's why the hydrogen's losing its
And it goes to this
losing its
bond.
electrons, and it's going to the bond that she's writing down.
Okay.
Yeah,
So
then
that's how the bond
oxygen is
breaks.
just gonna give
To the, yeah,
To the
to the
hydrogen.
They're gonna
hydrogen.
share those
Lost
electrons
its
to make another
electrons.
bond. But oxygen has two lone pairs, not one.
I don't think.
I'm sorry.
Yeah.
Give it a negative charge. Give the formal charge a -1 because 4.
Yeah, that's right.
There we go. Alright, so then this is the slow.
Slow step completed.
And now we're going to do the fast.
Transition state is
Okay, so we made a quick little mistake. The slow step was the loss of the chlorine with the potassium, and the fast step is the hydrogen making that double bond with the alpha carbon, and the hydrogen leaving with that OH group to make water.
the least.
So now we'll show the final product.
This product is said. So
Right?
a small base can come.
So this is a Zaitsev product, but why?
I thought it was because of a carbocation.
Okay, even imagine.
I thought it was because the major product is a Zaitsev product whenever it's the most substituted beta carbon that provides the proton for a double bond.
Because the opposite is the
Why don't we just look it up?
Yeah, the Hoffman's only
Does this say?
72. And it's the E1 mechanism.
Hydrogens and hydrogens are really small. So if the
Yeah, you're right. The more substituted product is preferred according to Zaitsev's rule.
But they're both like.
But then they were talking about how
That's what Ewan said on the note she
they
gave.
make the same product, so technically they're identical carbons. So like if you use one or the other, it'll give you the exact same thing. All you have to do is flip it over,
Yeah.
and it becomes the same thing.
Yeah, you can't squeeze in those small.
Oh, you know what? I was looking at here because it said in order to form the Zycev product, a carbon cation must form first. And so that's just why the product, how it formed. So,
E1 always forms Zaitsev.
yeah.
Okay, so just draw the.
The product.
Mm-hmm.
No, this is saying which of the following bases. So when you look here, when you look at how that is drawn, you have C double bond O L I.
So
So the L
Hold on.
has a partial positive charge, and then the
Sorry,
carbon
guys.
has a partial negative charge. So the carbon
CCH
can act as a
3
nucleophile or a base.
CCH 3 3.
How substituted is the
Awesome.
So we have to add.
Double bond.
No, yeah.
Whereas this one has two, whereas this one
Double
has
bond.
one big group and two
Going from one of the beta carbons to the alpha carbon.
has a method.
So it can either go there. Well, the way that we drew it on the last step, though, it would have to go there.
Yeah.
But if we drew the other
It
hydrogen,
would go on the bottom.
then it would go right here,
Yeah.
Yeah.
right?
So depending where that hydrogen like broke
Came
its
from.
bond or where it came from, that's where the double bond forms.
Yeah,
But they're the same. But they're identical.
So
yeah.
it doesn't matter.
Yeah.
Okay.
And what else? And then it formed water.
As well. Yeah.
That's just the other product.
Yeah. Just
The other. And that's
there we
it.
go.
That makes so much sense now.
It does.
It does a lot.
So just to summarize, yeah. What did you say about the E1 again? About the E1s, Zaitsev.
Oh.
Oh,
Well, E1s will always form Zaitsev products, and Zaitsev products are the major products that get the hydrogen from the most substituted beta carbon. So like if beta carbon has 2 hydrogens versus another beta carbon having 3 hydrogens, it would the carbon with the 2 hydrogens would donate its proton. But because these are identical, it doesn't matter which one the
Yeah.
proton is donated from.
You just have to remember where to put the double bond, depending on which hydrogen you remove.
Yeah.
yeah.
Or which bond you break, I guess. Hydrogen bond.
Yeah.